Welcome to this video on the states of matter. Are you ready to explore the fascinating world of matter? From the solid ground beneath our feet to the gases that fill our atmosphere, matter is all around us and comes in many different forms. But have you ever stopped to think about what exactly these different forms are? In this video, we'll delve into the world of the states of matter and explore the three main types: solid, liquid, and gas. You'll learn about their unique properties and characteristics, and discover why they behave the way they do. So grab a seat and get ready to be amazed by the incredible diversity of matter. Whether you're a science buff or just starting to learn about these concepts, this video is sure to fascinate and educate you. So let's get started and explore the wonders of the states of matter. The states of matter are a fundamental concept in physics and chemistry that describe the different ways in which matter can exist. At its core, matter is composed of atoms and/or molecules, which are the building blocks of all physical substances. However, the way in which these atoms and molecules are arranged and behave can lead to different states of matter. Here are the three main states of matter. Solid. In a solid, the atoms and molecules are closely packed into a fixed position relative to each other. This means that they do not change position or configuration unless an external force is applied. Solids have a defined shape and volume, and they retain their shape even when the external forces are removed. Examples of solids include metals, rocks, and ice. Properties of solids: have a fixed shape and volume, are hard and rigid. Do not change shape when an external force is applied or held together by strong intermolecular forces. Liquid. In a liquid, the atoms and molecules are close together but are free to move past each other. This means that they can flow and take on the shape of their container. Unlike solids, liquids do not have a fixed shape or volume, and they can flow easily when an external force is applied. Examples of liquids include water, oil, and alcohol. Properties of liquids: have a fixed volume but no fixed shape, are soft and flexible, can flow easily when an external force is applied or held together by relatively weak intermolecular forces compared to solids. Gas. In a gas, the atoms and molecules are widely spaced and are free to move in any direction. This means that they can expand to fill their container and can move freely without restriction. Gases have neither a fixed shape nor fixed volume, and they can be easily compressed and expanded. Examples of gases include air, helium, and hydrogen. Properties of gases: have neither a fixed shape nor fixed volume, are light and easily compressible, can expand to fill their container, are held together by relatively weak intermolecular forces compared to solids and liquids. It's worth noting that these states of matter are not mutually exclusive, and it's possible for a substance to exist in more than one state of matter. For example, water can exist as a solid, ice, liquid, water, or gas, water vapor. The state of matter of a substance is determined by the temperature and pressure at which it is found. In conclusion, the states of matter are an essential concept in understanding the physical world around us. By understanding the properties of solids, liquids, and gases, we can better comprehend the behavior of matter and how it interacts with its environment. Whether it's the way that water freezes in ice, the way that gasoline burns in a car engine, or the way that air moves through our lungs, the states of matter play a vital role in many of the processes that make our world function. The Bose-Einstein condensate, BEC, is a state of matter that occurs when a group of bosons, particles with integer spin, are cooled to extremely low temperatures, near absolute zero, 0 Kelvin or minus 273.15 degrees Celsius. At these temperatures, a large fraction of the bosons occupy the lowest energy state, at which point macroscopic quantum phenomena become apparent and the condensate behaves as a single entity. The concept of BEC was first proposed by Subtindran Bose in 1924 and was later developed by Albert Einstein. BEC is a unique state of matter that is different from solid, liquid, or gas, and it has several distinct characteristics. Single-phase nature. BEC is a homogeneous and single-phase material, meaning that all the bosons are in the same quantum state. Microscopic quantum phenomena. At BEC temperatures, the condensate exhibits microscopic quantum phenomena, such as coherence and quantum entanglement, which are not observed in classical systems. Zero viscosity. BEC has zero viscosity, which means that it can flow without any resistance. Non-classical statistics. BEC is described by non-classical statistics, such as Bose-Einstein statistics, which are different from the classical statistics used to describe gases. Quantum self-trapping. BEC can be self-trapped in a potential minimum, which allows for the manipulation of the condensate through a series of optical and magnetic fields. Highly sensitive to external stimuli. BEC is highly sensitive to external stimuli, such as changes in temperature, pressure, or magnetic fields, which can cause the condensate to undergo dramatic changes in its properties. BEC has several potential applications, including Quantum computing. BEC can be used to create ultra-cool qubits, quantum bits, that can be used for quantum computing and simulation. Quantum communication. BEC can be used to create quantum channels for secure communication, as the condensate can be used to encode and decode quantum information. Quantum metrology. BEC can be used to make precise measurements of physical quantities, such as magnetic fields or gravitational waves, due to its highly sensitive nature. Atomic clocks. BEC can be used to create ultra-precise atomic clocks, which can be used for timekeeping and navigation. Quantum optics. BEC can be used to create highly non-classical light states, such as Schrödinger cat states, which can be used for quantum communication and computation. BEC is typically created using a technique called laser cooling, which involves using lasers to slow down the motion of atoms or molecules, and then cooling them further using a process called evaporative cooling. The process of creating a BEC is highly complex and requires extremely low temperatures and high-resolution techniques. In summary, the Bose-Einstein condensate is a state of matter that occurs at extremely low temperatures, near absolute zero, where a large fraction of the bosons occupy the lowest energy state, leading to macroscopic quantum phenomena and unique properties. BEC has potential applications in quantum computing, communication, metrology, atomic clocks, and quantum optics, and it is created using laser cooling and evaporative cooling techniques. Fermi condensate, also known as a Fermi gas, is a unique quantum state of matter that occurs when a gas of fermionic particles, such as electrons or neutrons, is cooled to extremely low temperatures. In this state, these particles behave collectively as if they were a single quantum entity. At such low temperatures, according to the principles of quantum mechanics, fermions occupy lower energy states in a way known as the Pauli exclusion principle, which states that no two fermions can occupy the same quantum state simultaneously. As the temperature decreases, these fermions progressively fill up lower energy states until they reach the lowest possible energy state, known as the ground state. The concept of Fermi condensate is closely related to Bose-Einstein condensate, BEC. Both BEC and Fermi condensate are examples of quantum degenerate gases, where the quantum effects become dominant on a macroscopic scale. The key points that compose Fermi condensate are quantum degeneracy. The fermions condense into the lowest energy states available, forming a macroscopic quantum state. Pauli exclusion principle. Fermions, being particles with half-integer spin, obey the Pauli exclusion principle, which prohibits multiple fermions from occupying the same quantum state. Temperature. Fermi condensation occurs at extremely low temperatures, typically close to absolute zero, 0 Kelvin or minus 273.15 degrees Celsius. Density and interaction. The behavior of a Fermi condensate is influenced by the density and interaction strength between the fermions in the gas. Applications. Fermi condensates have applications in various fields, including quantum computing, precision measurements, and simulating complex quantum systems. The physics behind Fermi condensate involves the application of quantum statistical mechanics and the understanding of quantum behavior in many-body systems. It requires a comprehensive understanding of quantum mechanics, statistical physics, and condensed matter physics. Supersolid is a hypothetical state of matter that combines properties of both solid and superfluid. In this state, atoms or molecules arrange themselves in a solid-like lattice structure while also exhibiting superfluid behavior, which means they can flow without any friction. The concept was first proposed in the 1970s, and experimental evidence for supersolidity was reported in 2004 with ultra-cooled atoms trapped in optical lattice. The physics behind supersolidity is still an active area of research, and there isn't a full consensus on its existence. The theoretical understanding involves complex quantum phenomena, such as quantum phase transitions in Bose-Einstein condensation. These quantum effects play a crucial role in the behavior of atoms or molecules at extremely low temperatures, where they can display both solid and superfluid characteristics simultaneously. While there have been intriguing experiments suggesting supersolidity, the scientific community continues to investigate and explore this fascinating state of matter to gain a deeper understanding of its underlying principles. High-energy states refer to energetic states of matter or systems with particles possessing significant amounts of energy. In physics, these states are often associated with extreme conditions, such as high temperatures or intense forces. Here's a detailed explanation of high-energy states and the physics behind them. High temperatures. At high temperatures, the kinetic energy of particles increases significantly, causing them to move more rapidly and collide with greater force. High-energy states can be found in extreme environments like the core of stars, during high-temperature plasma experiments, or in particle accelerators. Plasma state. Plasma is an ionized gas consisting of positively charged ions and free electrons. It is an example of a high-energy state where the thermal energy is sufficient to strip electrons from their atoms. Plasma is prevalent in stars and other astrophysical objects and is used in fusion research in various industrial applications. Particle accelerators. Particle accelerators, like the Large Hadron Collider, LHC, accelerate particles to near light speeds and collide them. These collisions generate high-energy states, allowing scientists to study fundamental particles and their interactions, helping to unveil the underlying structure of matter. Quantum excitations. In quantum mechanics, particles can exist in excited states with higher energy levels. For example, electrons in atoms have discrete energy levels and can jump to higher energy states when absorbing energy. This phenomenon is fundamental to understanding the behavior of atoms and molecules. Nuclear reactions. Nuclear reactions, like fusion and fission, release enormous amounts of energy. In nuclear fusion, light atomic nuclei combine to form heavier nuclei, releasing tremendous energy, as seen in the process that powers stars. Black holes. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape their pull. Matter falling into a black hole experiences extreme compression and temperature, leading to high-energy states. High-energy cosmic events. Cosmic events like supernovae and gamma-ray bursts produce incredibly high-energy states. These events involve the release of vast amounts of energy during the explosion of massive stars or the collision of neutron stars. Quantum field theory. High-energy states are studied extensively in quantum field theory, where particles are described as excitations of underlying quantum fields. The interactions between these fields at high energies give rise to various phenomena in particle physics. Understanding and studying high-energy states play a crucial role in advancing our knowledge of the universe and the fundamental laws of physics. They offer insights into the behavior of matter under extreme conditions, helping us unravel the complexities of nature at its most energetic scales. Degenerate matter is a unique state of matter that occurs under extreme conditions, typically at very high densities and low temperatures. It is governed by quantum mechanical effects and behaves differently from ordinary matter found in everyday environments. Let's explore each point that composes degenerate matter in detail. Extreme density. Degenerate matter is incredibly dense, with particles closely packed together. This high density can be found in the cores of certain massive celestial objects like white dwarfs, neutron stars, and possibly in the interiors of some exotic planets. Quantum degeneracy pressure. In degenerate matter, quantum mechanical effects dominate, and the Pauli exclusion principle comes into play. This principle states that no two fermions, particles with half-integer spin, can occupy the same quantum state simultaneously. As matter becomes denser, electrons, for example, are forced into higher energy states due to this exclusion principle, generating a pressure known as quantum degeneracy pressure. Low temperatures. Degenerate matter is usually associated with very low temperatures, as seen in the remnants of massive stars like white dwarfs and neutron stars. At these low temperatures, thermal energy is not sufficient to overcome the quantum degeneracy pressure. White dwarfs. White dwarfs are the remnants of low to medium mass stars that have exhausted their nuclear fuel. In this stage, the star's core collapses, and electrons are compressed so densely that they become degenerate matter, supporting the star against further gravitational collapse. Neutron stars. Neutron stars are extremely dense stellar remnants primarily composed of neutrons. In the core of a neutron star, the pressure from degenerate neutrons resists gravitational collapse. Neutron stars can result from the supernova explosion of massive stars. Exotic physics. Degenerate matter often exhibits exotic and bizarre phenomena due to its quantum nature. Neutron stars, for instance, can have incredibly strong magnetic fields and emit beams of radiation from their poles, resulting in observable pulsars. Fermi-Dirac statistics. Degenerate matter is described by Fermi-Dirac statistics, which govern the distribution of fermions in quantum states at low temperatures. These statistics are essential in understanding the behavior of electrons and other fermionic particles in degenerate matter. Degenerate matter is a fascinating and essential field of study in astrophysics and condensed matter physics. It helps us better comprehend the behavior of matter under extreme conditions, revealing the mysterious and intriguing nature of the universe's densest objects. Strange matter is a theoretical form of matter that is composed of strange quarks, one of the 6 types of quarks found in particle physics. Strange quarks are heavier and more unstable than the up and down quarks that make up protons and neutrons. When these strange quarks are bound together, they form a hypothetical form of stable matter known as strange matter. Here are the points that compose the concept of strange matter in detail. Strange quarks. Quarks are elementary particles that are fundamental building blocks of matter. They come in 6 types or flavors: up, down, charm, strange, top, and bottom. Strange quarks are one of the 3 types of quarks that are heavier and less common in the universe compared to up and down quarks. Strange matter hypothesis. The strange matter hypothesis suggests that when enough strange quarks come together and form a bound state, they could create a type of stable matter known as strange matter. Unlike other types of matter, strange matter is theorized to be stable even at extreme conditions like high densities and pressures. Strangeness. Strangeness is a quantum property associated with strange quarks. Particles containing strange quarks have non-zero strangeness, and the conservation of strangeness plays a crucial role in various particle interactions. Strange quark stars. One of the most intriguing possibilities related to strange matter is the concept of strange quark stars. These are hypothetical celestial objects composed almost entirely of strange matter. They are thought to be denser than neutron stars and may form in the aftermath of a supernova explosion of massive stars. Quark-gluon plasma. At extremely high energies and temperatures, quarks and gluons, which are the particles responsible for the strong force that binds quarks together, may exist in a confined state known as quark-gluon plasma. This state is believed to have existed in the early universe just moments after the Big Bang. Detection and observations. As of my knowledge cutoff in September 2021, strange matter has not been observed or definitively detected. However, scientists continue to study and explore its properties through experiments with high-energy particle colliders and astrophysical observations of compact stellar objects. It's important to note that strange matter remains a theoretical concept, and further experimental evidence and observations are required to confirm its existence. The study of strange matter is a fascinating area of research in particle physics and astrophysics, providing valuable insights into the fundamental building blocks and behavior of matter in the universe. Photonic matter generally refers to a system or medium where photons, the elementary particles of light, interact with each other in a collective manner, resembling the behavior of particles in conventional matter. Slow light. In certain materials, such as Bose-Einstein condensates, BECs, or specially engineered media, light can be significantly slowed down, and its behavior can be governed by interactions between photons. This slow light can be considered a form of photonic matter. Polaritons. Photons can strongly interact with matter, leading to the formation of hybrid particles called polaritons. These polaritons have properties of both photons and material particles, and they can exhibit behaviors similar to those of conventional matter. Photonic crystals. Photonic crystals are periodic structures that can manipulate the propagation of light and control its behavior in certain ways. These structures can exhibit properties of matter by affecting the flow of photons. Quantum optics. In the context of quantum optics, researchers study how light behaves at the quantum level and how photons can interact and be manipulated for various applications, including quantum information processing. Quantum electrodynamics, QED. QED is the quantum field theory that describes the interactions between photons and charged particles. Photons are the carriers of the electromagnetic force, and their behavior is a fundamental aspect of QED. It's important to note that the term photonic matter might be used differently in specific research areas, and its meaning could evolve as scientific knowledge progresses. As research in the field of photonics and quantum optics advances, the concept of photonic matter may become more well-defined and understood. Quantum spin liquid is a fascinating and elusive state of matter that arises from quantum interactions between magnetic moments, known as spins, in certain materials. Unlike conventional magnetic materials, quantum spin liquids do not exhibit long-range magnetic order even at very low temperatures. Instead, the spins remain in a highly entangled and fluctuating state, giving rise to unique quantum behaviors. Here are the key points that compose the concept of quantum spin liquid. Spin interactions. Quantum spin liquids emerge from the quantum mechanical interactions between the spins of atoms or ions in a material. These spins have an intrinsic property known as spin, which is a measure of their angular momentum. Frustration. Quantum spin liquids are often found in materials where the spin interactions are frustrated. Frustration occurs when it is impossible for all the spins in the material to simultaneously satisfy their interactions in a way that minimizes the total energy of the system. This frustration prevents the spins from aligning in a regular pattern, leading to a disordered or fluctuating state. Absence of magnetic order. In conventional magnetic materials, spins align in ordered patterns to create magnetic moments that result in long-range magnetic order. In a quantum spin liquid, the spins remain disordered and do not form a well-defined magnetic pattern, even at very low temperatures. Exotic excitations. Quantum spin liquids are known for their exotic excitations, such as fractional Iskaside particles. These quasi-particles can carry fractional values of a spin, a phenomenon not observed in conventional magnetism. Topological order. Some quantum spin liquids are believed to possess topological order, a unique type of order that is not described by conventional symmetries, but instead relies on global features of the material structure. Quantum entanglement. Quantum spin liquids are highly entangled states where the quantum correlations between spins extend over long distances. This entanglement plays a crucial role in the emergent behaviors of the material. Theoretical framework. The understanding and description of quantum spin liquids involve sophisticated theoretical tools such as quantum field theory, Gibbs theory, and topological quantum field theory. Experimental challenges. Identifying and characterizing quantum spin liquids experimentally is challenging due to their elusive and unconventional nature. Researchers use various experimental techniques, including neutron scattering, nuclear magnetic resonance, and thermodynamic measurements, to study these materials. Applications and potential. Quantum spin liquids hold promise for applications in quantum computing and information storage due to their unique quantum properties and fractionalized excitations. However, practical applications are still in the early stages of exploration. Quantum spin liquids represent a cutting-edge field of research in condensed matter physics. Understanding their properties and behaviors is essential for advancing our knowledge of quantum matter and may lead to breakthroughs in quantum technologies in the future. Liquid crystals are a state of matter that exhibits properties of both liquids and crystalline solids. They have intermediate characteristics between the highly ordered structure of a solid and the fluidity of a liquid. Liquid crystals are composed of elongated molecules or particles that can align themselves in a specific direction while still maintaining some degree of mobility. Here are the key points that compose the concept of liquid crystals in detail. Molecular alignment. The molecules or particles in a liquid crystal are elongated and of a preferred orientation. While they have some degree of order, they are not as strictly arranged as in a crystalline solid. Anisotropy. Liquid crystals exhibit anisotropic properties, meaning their physical properties differ depending on the direction they are measured. This anisotropy arises from the preferred alignment of the molecules. Phases. Liquid crystals can exist in different phases, such as nematic, symmetric, and cholesteric phases, depending on the level of ordering and molecular arrangement. Each phase has distinct characteristics related to the alignment and motion of the molecules. Responsive to external fields. Liquid crystals are responsive to changes in temperature, pressure, and electric or magnetic fields. These external influences can cause phase transitions and alter the orientation of the liquid crystal molecules, leading to changes in their optical and electrical properties. Optical properties. Liquid crystals have unique optical properties due to their anisotropic nature. They can change the polarization of light passing through them, making them useful in various display technologies like liquid crystal displays, LCDs, commonly used in electronic devices. Electro-optic effect. The electro-optic effect is a crucial property of liquid crystals where the alignment of the molecules can be controlled using an electric field. This phenomenon enables the operation of LCDs, allowing the manipulation of transmitted light to create images. Flexoelectricity. Liquid crystals can exhibit flexoelectricity, where the application of mechanical strain or curvature generates an electric field and vice versa. This property is essential in some display technologies and to their applications. Biological significance. Liquid crystals are found in living organisms as well. For example, certain biological tissues, like cell membranes and collagen fibers, exhibit liquid crystalline behavior, contributing to the organization and structure of living organisms. Applications. Liquid crystals have numerous practical applications beyond LCD technology, including in optical devices, tunable lenses, sensors, and switchable windows, among others. Liquid crystals have revolutionized various technologies, especially in the field of displays. Their unique combination of ordered structure and fluidity makes them versatile and highly useful for a wide range of applications across industries and scientific research. Goodbye.